Hello, welcome to my talk. This is the second part of the water wave in finite water depths, and the main focus in this talk is on the water wave motions in different water depths, and on wave propagation from deep water to finite water depth, then to shallow waters, and we will see when and how the wave showers and finally breaks on the beach. We have obtained the wave velocity potential function in finite water depths in the part 1 of the talk on this topic, which is given in this form. Here, h is the water depth. And this wave velocity potential function is very important, and in this talk, we will use it to study all the wave characteristics. Based on this velocity potential function, we can deduce that the water wave is not just on the water surface, but also in water, and the wave in water can be easily obtained from the linearized Bernoulli's equation, given as this. Here, the wave amplitude in the red ellipse is dependent on the vertical position, z in water. So if we take z equals 0, we can obtain the wave on the water surface expressed as this. So consider an example of a wave amplitude of 4 meters and a period of 8 seconds in water depths h equals to 20 meters. Such a wave is a very large wave, and I will use this example to illustrate the waves in a finite water depth. Based on the dispersion relation, we can calculate the wavelength in such a water depth. It is 88.84 meters. For a comparison, the wavelength in deep water is given lambda 0 equals to 99.84 meters, and the relevant wave number can be easily calculated as this. It's about 0.07. And based on this, we can calculate the wave amplitude in water. See this plot. From this figure, we can see the wave amplitude on the water surface is 4 meters, and the wave amplitude decreases with the increase of the vertical position in water. And at the seabed, the wave amplitude is given as this. We can see the wave amplitude at the seabed is not 0, but dependent on the water depth h. Of course, if h is large enough, the wave amplitude at the seabed would be 0. In details, we can calculate the wave amplitude for different z given here. So we have different z. The corresponding wave amplitude would be 4.0 on the water surface, and at z equals to -5, the amplitude would be slightly smaller than 3 meters. And at z equals to -15 meters, the wave amplitude is slightly less than 2 meters. So if we draw these waves in the water, we can see the different wave at the different z. In this plot, the water depth, the wave amplitude, and the vertical positions are all proportional correctly. If we compare the same wave in deep water at z equals to -15 meters, the wave amplitude is only 1.56 meters. So we can see in deep water, the wave amplitude decays quicker. Based on the wave velocity potential function, we can calculate the water particle motion, the horizontal and the vertical velocity u and w. This is based on the differentiation of the wave velocity potential function with regard to x and with regard to z respectively. So we can see the wave velocity component u and w has a phase difference of 90 degrees, indicated by this imaginary unit I here. If we draw out of the velocity vector, and we can see the velocity vector would depend on z, the vertical position in water, and the phase given by kx minus omega t. So we can see the water particle velocity components are proportional to both the wave amplitude and the wave frequency. And we can also see u and w have different amplitudes. In the expression, the different numerator, Cauchy function and singe function here. If in deep water, h would be very large. Thus, we have the approximation at this Cauchy k z plus h equals singe k z plus h, and given by an expression as this exponent. And the singe kh can be expressed as this. So use this approximation, we can obtain the relation for this, and this we are given for this exponent. Therefore, in deep water, the velocity component u and w can be expressed simply as this. These are same as those we have seen in the previous talk on linear wave theory. From the expression of the velocity components, we can integrate them with time to obtain the water particle position x and z as this. Again, we can see these two components would have a phase difference indicated by this imaginary unit. And we write this expression into the real values. It would be like this. And this is the same as the trajectory equation given by this. So this is an equation for an ellipse. This means the water particle motion in finite water depth is an ellipse, see in here. However, if h is very large in deep water, means we have this approximation. And then this ellipse would have the same length on x and on y, and this ellipse would become a circle. This means in deep water, the water particle motion would be a circle. This is the same as we have seen in the talk on linear wave theory. In this slide, we will see what is the condition for distinguishing the deep water and the finite water depths for ocean waves, as it is well accepted when the water depth is equal to or larger than half of the wavelength, which could ensure the approximation of this expression. And when h is equal to or larger than half of the wavelength, the maximum error would be less than 0.366% for this approximation. So this is actually very accurate for engineering applications. So in deep water, the dispersion relation can be simplified as this. Here, the subscript 0 is used to indicate the parameters in deep water, and we can obtain the wavelength lambda 0, the phase velocity Vp0, and the group velocity Vg0 expressed as this formula. If we take a wave of a period of 10 seconds as an example, the wavelength in deep water is 156 meters, and the condition for deep water is the half of the wavelength, h equals to 78 meters. So we use the approximation relation, we can calculate the phase velocity Vp0 and the group velocity Vg0. And in here we compare the actual wavelength, phase velocity, and the group velocity at the water depth 78 meters compared to the approximation given by these equations. So we can see the error would be 0.3660% and minus 1.89%. So again, we can see this approximation equation would be very accurate for these parameters. Especially, it would be very good for engineering applications. As such, we can assume when the water depth is equal to or larger than half of the wavelength, the water depth can be regarded as the deep water. Another limit condition is called shallow water condition, when the water depth is equal to or less than 1/20th of the wavelength. Under such a condition, the tension function can be approximated by this equation. Therefore, in the shallow waters, the dispersion relation can be simplified as this. Here, the parameters with the subscript 1 for indicating the parameters in shallow water. And we can see the wavelength would be proportional to the wave period, and the phase and the group velocity would be same. Both are constant if the water depth are given. If we take the same wave of a wave period of 10 seconds, in the shallow water, the water depth would be 2.375 meters, and we can compare the actual value and the approximations for the wavelength, phase velocity, and the group velocity. And it can be seen the errors for these parameters would be 1.6 to 2% and 4.9 to 4%. So we can see this is still acceptable for the engineering application. And this shallow water condition is corresponding to the shallow water wave condition given by this h equals lambda 0 divided by 65. Lambda 0 is the wavelength in deep water. The shallow water waves are important in coastal engineering applications, and the other important application would be for the tsunamis and the tides, for which the period are of tens, minutes, and hours, and both can be regarded as shallow water waves in the ocean. Use the wave potential function, we can calculate the water particle motion in shallow water. In shallow waters, when the water depth is smaller than 1/20th of the wavelength, the parameter kh would be small, less than pi divided by 10. Hence, we can have the approximations given here. If we substitute these approximations into the wave water particle velocity u and w, we can obtain the velocities of the water particles in shallow water given in this form u and w here. And if we draw out of the motion of the water particle, we can see the water particle motion is elliptic, and for different water depths, the ellipse length on x-axis would be a constant. It's independent of z, so we can see the drawing like this. So in this slide here, a summary of the water waves in different water depths is given. Principally, we have three regions for water waves: deep water, intermediate water depths, and shallow water depths. And in both deep water and shallow water, we have the approximation for the wavelength and the phase velocity here, the group velocity, this and this. But for the intermediate water depths, we have the accurate formula for the wavelength, phase velocity, and the group velocity. But all these are nonlinear equations which can be expressed by the approximations or solving using the iteration method. Here, we use the subscript 0 and 1 to distinguish the approximation values in deep water and in shallow water, respectively. The water particle motion are also different in different water depths. In deep water, the water particle motion is a circle, and the size of the circle decreases with the increase of the vertical position in water. But in finite water depths, the water particle motion is elliptic, and in shallow water, the horizontal size of the ellipsis is a constant, independent of the vertical position z. In the next two slides, the wave shoaling is examined. Wave shoaling means when wave travels from deep water to shallower water, the waves change forms during the propagation. Based on the energy conservation, here the wave energy loss due to its interaction with the seabed is small and neglected. The wave shoaling coefficient Ks is the ratio of the wave height in the finite water depths over that in deep water H0. The ratio would be given as the square root of the wave energy velocity Vg0 over Vg. Vg0 is given in this form, and Vg is given in this expression. If we draw out of the shoaling coefficient Ks against the water depths for a wave of a period of 10 seconds, we can see the shoaling coefficient decreases first when the wave propagates from the deep water to finite water depths here, and then increase when it travels to shallower water. In details, from the plot, we can see the wave starts shoaling at about h equaling to half of the wavelength, and the shoaling coefficient starts to decrease with the decrease of the water depth until the water depth reaches 1/6 of the wavelength. Then the shoaling coefficient increases with the decrease of the water depth. In theory, the shallower the water depth, the higher of the wave height. However, in reality, wave would break when its height reaches a certain criterion. See the next slide. This is the drawing of the wave propagation from deep water to shallow water. The wavelength becomes shorter and the wave height becomes larger. And this can be seen from this photo. If we look at far away from the beach, the sea surface is very calm, where the wave height is small. When the wave comes to the shallow water close to the beach, and we can see the wave height is increasing due to the wave shoaling. For ocean waves, if the ratio of the wave height over the wavelength is larger than a certain value, the wave would break. A most accepted criterion is the general limit for ocean waves, given in this form, which gives the maximum possible wave height for a given wave period, and the wave would break if the wave height is too large compared to the wavelength. So in deep water, the tension function would be a unit. Thus, the ratio of the wave height over the wavelength would be 1/7 in deep water. And in shallow water, the tension function can be approximated by this expression. And we have the expression as this, and we can write the expression as this. This means in shallow waters, the ratio of the wave height of the water depth cannot exceed 0.9. In the next 3 slides, we will examine the physics of the wave breaking, and we will see what is the physical process or physical condition when wave breaking happens. Take a wave of a period of 10 seconds as an example. In deep water, the wave length, phase, and the group velocities would be 156 meters, 15.6 meters per second, and 7.8 meters per second, respectively. And based on the wave breaking criterion, the maximum wave height would be 1/7 of the wavelength, calculated as 22.28 meters. Thus, the maximum wave amplitude would be 11.14 meters. For such a wave, the maximum horizontal velocity of the water particle can be calculated U max equals to A omega at 7 meters per second. So if we compare U max to the group velocity Vg0, we can see the wave breaking criterion in deep water means when the maximum physical velocity U max is approaching to the energy transfer velocity Vg0, the wave breaks. The same wave is for shallow water condition. Here, water depth would be 2.375 meters. The accurate wavelength, wave phase, and the group velocity are given as this: 47.5 meters, 4.75, and 4.6 meters per second, respectively. And based on the criterion, the maximum wave height would be calculated as this 0.9 water depth. It would be 2.14 meters. Hence, the maximum wave amplitude would be 1.07 meters. Then we can calculate the water particle horizontal velocity Umax given as this formula. It is 2.14 meters per second. And in the shallow water, if we compare Umax and Vg1, we can see when Umax approaches to half of the global velocity in shallow water, the wave breaks. Let's look back to the general wave breaking criterion, and we first examine the hyperbolic function, the tangent function. We can see from this plot the tangent function, it's a unit in deep water here, and the tangent function decreases when the water depth is smaller than the half of the wavelength, and the shallower the water depth, the smaller the tangent function. Therefore, it can be understood when the wave propagates from the deep water to shallower waters, the limit of the ratio of h over lambda becomes smaller and smaller, less than 1/7, other than the ratio is 1/7 in the deep water. In the shallow waters, when the maximum horizontal velocity Umax approaches to half of the wave global velocity Vg1, the wave breaks, while in the deep water, Umax approaches to the global velocity Vg0. In this slide, we will examine the wave breaking modes. In reality, wave breaking is a very complicated process, and so far, the numerical modeling and the physical modeling would be difficult. Here, we follow some simple principle to look at the wave breaking in shallower waters or on beaches. For this purpose, we introduce a non-dimensional number called equilibrium number, Ni, given in this formula. So for different slope of the beach and the wave height and the wavelength, we may have different wave breaking modes. On the beaches of a small slope, where the equilibrium number would be small, say less than 0.5, the wave breaking would be spilling, see in this picture. The wave breaking happens when the crest spills forward until it is all white water, thus the wave energy dissipates. When the slope of the beach increases, the equilibrium number is between 0.5 and 3.3. The wave breaks in a form called plunging, especially when the wave's crest curls over and explodes on the trough, as we have seen the cool picture here. In the steeper beaches, when the equilibrium number becomes larger than 3.3, the wave breaks either in collapsing or surging. In surging, the wave hardly breaks due to the steeper beach and the relevant large water depth, so the wave surges back to the sea. In an extreme condition, with a vertical wall of the sea front, the wave would be fully surged back to the sea, while the collapsing is between the surging and plunging. with some weak wave breaking and the corresponding wave energy dissipation, while some other wave would return back to the sea. See this picture and this one.